Let's start with the statement of the intermediate value theorem. This is going to be very technical, and then we're going to rephrase it in a little more English-friendly way. So, if f is continuous on the closed interval a to b, f of a does not equal f of b, and k is any number between f of a and f of b, then there exists at least one number c in the interval a to b, that's for x, such that f of c equals k. Another way to say this if f of x is continuous on the interval a to b, and this is x values, the curve must pass through every value for y between f of a and f of b at least once. Now the key thing here is this is only true if f of x is continuous. So this is really, really, really important. Let's do a little diagram of that. I think that'll help it be clearer. So let's say we've got some value a, some value b. This is on the x-axis. And this is f of a, just some value. And this is f of b, so some value right there. What this is saying is it's saying that if this is continuous, then in order to get from this dot to this dot without lifting our pencil, we have to go through every value in between here. So if I pick some value, k, no matter how I twist and strain, as long as this is a continuous function, at some point there's some value c for x, that when x equals c, y equals k. That's what it's saying. No matter how we strain and strain and strain and strain, if this is a continuous function, we've got to go through all of these numbers here. All of these have to get hit at some point. Now, it may be the case that the curve passes k multiple times. Let's say we've got our same little drawing here. Maybe the function goes like this, woo, woo, and goes something like that. That's entirely okay. Notice that this says at least once. The big thing, though, is that this is not true if f of x is not continuous. So in that case, let's say we had something like this. This number k there's no value between a and b at which y equals k. Okay, this is spiffy, but why do we care? The intermediate value theorem is particularly useful for narrowing down where the zeros of a function are. If a function is continuous, and f of a is less than 0, and f of b is greater than 0, or vice versa, then f of x must have a 0, for some x on the interval a comma b. So for example, let's say that this is a, this is b, we have this dot here, we have this dot here. Somewhere, if this is a continuous function, there's got to be a 0 somewhere. We don't know if it's here, we don't know if it's here, we don't know if it's here. This could, remember, there could be multiple zeros, it could be looping up and down like that. But there's got to be a 0 somewhere in here, because if this is a continuous function, there's no way to get from a negative value for y to a positive value for y without at some point going through 0. And so this was actually used before there were more exact techniques to just kind of narrow down where a 0 was. Because basically you would just take numbers that were closer and closer and closer and closer to each other, and if one was negative, one was positive, there had to be a 0 in between. And just kept doing that until mathematicians got the precision that they wanted for the 0. And being able to find zeros is very, very important in the graph analysis unit, because zeros of a derivative are going to be used to tell us when we have a maximum and minimum for a function itself. And this is something that is incredibly useful in real-world situations. Let's use the intermediate value theorem for a couple of problems. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0, 1. So a key thing to know, a polynomial function, polynomial function, a polynomial function by definition is continuous. A polynomial function is really just something like this. F of x equals 3x to the fourth plus 2x squared minus 5x plus 1, or something like that. It's just a polynomial, basically. So we're using the intermediate value theorem to show that there's a zero. So basically we just want to show that one end of the interval is positive, one end of the interval is negative. F of 0 equals 0 cubed plus 2 times 0 minus 1. F of 0 equals negative 1. F of 1 equals 1 cubed plus 2 times 1 minus 1. F of 1 equals 2. Because f of 0 is less than 0 and f of 1 is greater than 0 and f of x is continuous, the intermediate value theorem indicates that for some value x equals c on the interval 0, 1, f of c equals 0. Ta-da! That's it. We can also do similar problems with graphs, or excuse me, with tables, if f of x is a continuous function. And has some values given in the table. Here's x, here's f of x, -3, 0, 1, 2, 5, 1, 3, -2, -6, and 4. What can we conclude? About the locations of zeros of f of x. Well, because f of x is continuous, and f of 0 is greater than 0, and f of 1 is less than 0, f of x must have at least one 0. Could have more. On the interval 0, 1. Likewise, notice that when x equals 2, f of x is negative. When x equals 5, f of x is positive. So we've got a similar situation there. There must be at least one 0. On the interval 2, 5, because f of 2 is less than 0 and f of 5 is greater than 0. There may be additional zeros, but these ones we have to have. So like here, maybe f of x is positive at x equals -3, negative at x equals -2, and positive again at x equals 0. So there might be additional ones, but these are the only ones that we know for certain have to be there. Note again, if we weren't told f of x is continuous, We couldn't conclude anything. Because if it's not continuous, maybe these are the only points on there. Let's do a check for understanding problem with that type. F of x is a function, some values of which are given in the table. One, two, three, actually 1, 2, 4. Three, -1, -5, -4. What can we conclude about the locations of these zeros of f of x? Okay, pause the video, try that one on your own, and then start the video up when you're ready. Okay, turns out this is a trick question. F of x is a function. It does not say anything about whether it is a continuous function. We cannot conclude anything. There may be no zeros at all. Perhaps these are the only 4 points in the entire function. If we were told that it was continuous, then we would be able to conclude that there is a 0 between x equals 1 and x equals 2 because there's a change in f of x from positive to negative here. But if we're not told it's continuous, nada, nothing.